Hello, everyone. In the last lecture, we talked about the logistic regression model, the maximum estimation for the logistic regression model, and how to optimize that by gradient-based approach. So we start from a linear regression model. So I call it CW transpose X plus B. Okay, so this is the output of a linear regression model. But in the classification case, especially for a binary classification, it's just the goodness of the sample to be the positive sample. So I mean, C by Z is, of course, it's an identity line. But if you use the 0 and 1 target to train the goodness by mean square error, then you are having a very large loss for the samples that can be very well predicted. So this is undesired. And now we are going to squeeze the function or squash the function into the region of 0 and 1, where the probability, the number is the predicted probability that your true target may be 1, okay? So I would say the prediction, now this time, my prediction Y is actually a sigma Z, where sigma is a sigmoid function like this, okay? And Z is still W transpose X plus B, okay? And this is interpreted as the probability, and actually it's the predicted probability that T is 1 given that data sample, okay, X. And we talk about the loss for the logistic regression, which is our cross-entropy loss. Okay, suppose your target is Tm for the M data sample, then the loss of your W and B is the summation over all data samples, or it may be the mean over the per sample loss, T log Y. Okay. So this is my cross-entropy loss. So now the question is, how is it compared with the mean square error loss? We know if you apply the mean square error loss on the samples, on the goodness, okay, which is a real number for the target, 0 to 1 target, it's not a good idea. You have too much penalty for these samples, okay? But can we just apply the mean square error loss on 0 and 1, okay? Is there any significant deficiencies if you just apply the mean square error on the squash function? Just like J, okay, mean square error for logistic regression model, I would say it's, okay, I don't mind whether it's half or not. Okay. So it turns out that obviously you can do that, but it may not give you the good result. And the reason is, what is your mean square error? So suppose my target is 0, okay? And if target is 1, it's symmetric. So now why not assume the target for a particular data sample is indeed 0, it's a negative sample. So the target is just 0, okay? The target is 0. And what is my y-axis? My y-axis is, the horizontal axis is y. Okay? So, and my vertical axis j. So j is actually a function of y. So it says, so this plot says, what is your loss based on your prediction? Okay. And I know y must be within the range of 0 and 1 because I'm predicting the probability. Okay. And it's indeed a probability. So the output must be within the range of 0 and 1. So what is the loss for mean square error? So now this time target becomes 0, okay? So it's basically, okay, y squared, okay, for some data samples m. So let's consider one particular m, then it's just this, okay? So how about the cross-entropy loss? The cross-entropy loss is if my target is indeed 0, then this term vanishes, okay? And I only have this term, so it becomes minus log of 1 minus ym, okay? Then what if your prediction is 0? So you say, my target is 0, and my prediction is 0. So your prediction is 0 means the probability of being 1 is 0. Then the probability of being 0 is 1, okay? Then it's very good. So if your prediction is 0, then it's a very good prediction for true negative sample. Then if it's 0, then it becomes log 1, so it's 0. Okay? So I'm saying the cross-entropy loss is this. But what if your prediction increases? Okay, it's not 0, but I would say 0.1. So if your prediction increases, then the 1 minus something decreases, okay? So this decreases and the log decreases, but it's minus log, so it increases, okay? So it also increases. So it looks similar to the mean square error. But what if my prediction is 1? Now I say y is 1, okay? Or maybe y converges to 1. You say the sample is indeed a negative sample, but I say it's almost sure that it's a positive sample. So it's a very bad prediction. Then if you put y equals 1 here, then it's log 0. It gives you minus infinity because log looks like this. And then it's minus log infinity, then it's infinity, right? So it tells me that the log is this, okay? This is my cross-entropy loss, and this is my mean square error loss, okay? So there's nothing wrong in terms of whether you would like to penalize a sample or not penalizing a sample, but the main issue is mean square error loss is too mild. It says no matter whether you predict 0 or 1, you are in this region and the mean square error loss gives you a loss less than 1, okay? It's just a small penalty, it's not a problem. But cross-entropy loss says, if you are 0, you are fine. It's the same as mean square error loss. But if your prediction is wrong, especially it's in the opposite polarity, it says, if the target is 0, but my prediction is 1, it's infinitely bad. Okay, it's infinitely bad. It gives you a very strong training signal that you should reconsider. Okay, so this is the comparison of the cross-entropy loss and the mean square error loss. Now we have another concern. Since the loss goes to infinity, is it possible that when we do the gradient-based update, my gradient blows up? Okay, it just means your gradient is too large, and if you do gradient descent, the loss goes to infinity. Okay, you are overshooting. So the calculation of the gradient suggests it will not occur because my gradient, so let's consider the partial derivative of my j of a particular sample with respect to, let's say z, okay, the goodness of a sample. And if I compute the partial derivative of j with respect to wi, then it becomes the partial derivative of j for that sample with respect to z of that sample, and then the partial derivative of z of that sample with respect to wi. Okay. So let's consider this part. And this part, we know this is xi for that sample, okay? So let's consider the first term. And based on our calculation, we know that it's y minus t. Right. You remember in the previous lecture, we talked about the gradient is x transpose y minus t, okay, as a vector t and a vector y. And this x serves as this multiplication. And the matrix multiplication serves as the summation over different samples. But consider one sample, then the gradient is just this, okay? So it shows that the gradient is linear in terms of how much error you make. Okay, if the target is indeed 0, and if your prediction is 0.1, then you have a gradient 0.1. If your target is still 0, but you predict at 0.9, then your gradient is 0.9. Okay, so the gradient is proportional to how different is your prediction versus the target. Okay. And we mentioned that the loss, increases drastically. It's even more quickly than the exponential, right? Because the exponential will not converge to infinity at this point, but now the log is some flip of the log curve is this part, okay? So it's increasing drastically. Okay. And the question is why? And it turns out that this is because of the chain rule of the derivative. So you see the derivative here is very, very flat. And this compensates to the increase of your loss, okay? This exactly cancels out the drastic increase of your loss. And eventually you will get the gradient proportional to your difference of your prediction, okay? So this is the reason. And for mean square error, you see, if you multiply this loss with your flat derivative of the sigmoid function, then the loss is almost negligible. So it shouldn't give you a good result. Okay. So it also turns out that when we implement the loss, especially if you're doing autodiff. So I just have a very brief introduction about autodiff. Autodiff is just, you compute, for example, Z based on W, and then you compute Y based on Z, and then you compute the loss, okay, based on Y. In modern neural network toolkits, for example, PyTorch or TensorFlow, you only need to define how the loss is computed. Then it automatically differentiates through the reverse computation of the variables, right? You just go back and then it gives you the gradient because of the chain rule. So if you apply the cross entropy loss on Y, it's a very bad idea. Okay? It's a very bad idea because it's very numerically unstable. Rather, you would like to apply some equivalent loss directly on Z. With that equivalent loss, you get the derivative equivalent to this, okay? In this way, your computation is much more numerically stable because you don't have to compute the exponential and then you cancel it out by some flat function. You just cancel them out mathematically in your derivation, okay? Then it's computationally more stable. Okay. So this is just some further thoughts on the cross-entropy loss for binary classification. So how can we do multi-class classification? So now we have multiple classes. Suppose my target is one of C1, C2 up to CK, okay? Or you can call it 1, 2 up to K. Okay, so my target is one of them. How can I apply the similar idea of logistic regression to do the classification? So first again, linear regression is not a good idea for almost the same reason as before. And also the target is rather not represented as 1, 2, 3, 4, 5 because you are introducing some artifact of the order or the distance, okay? So you'd rather predict the target as either C1 or not, or C2 or not, but you must predict one and at the most one category, okay? So applying a similar thought, I'm going to say, why not let's compute a goodness function, okay, for each category. Okay, is that fair? So I'm saying my sample has some features, okay? And then it indicates maybe it's a cat, maybe it's a dog, maybe it's an elephant, okay? Maybe it's also a mouse. Then I'm saying whether these features indicate that this animal is a dog or a cat, okay, separately. So I will compute Ci as the goodness of your function as Wi transpose X for some data sample n, okay, plus Bi. Okay. For I equals 1 up to k. For each category, I compute a goodness. But eventually, I will consider the goodness of different categories and I will make a prediction for one and only one category. So how can I do that? And again, I want to make a probability. So how can I make a probability from a real number goodness function? So eventually, I would compute the probability, okay, for a particular data sample. So I think I can ignore the M stuff. M is unimportant here. Okay. Eventually, I want to have a probability for different categories I. And for a probability, it must satisfy the Kolmogorov axioms, which means Pi is greater than or equal to 0 for any I from 1 up to k. Okay. And then the sum of different Pi's must be 1. Okay. Then how can I get a probability from a real number goodness? Okay. The trick is you take the exponential, then it's all positive. Then you normalize it, then it sums to 1. Okay, so this is the trick. So 2-step. First, I compute the probability Pi tilde is the exponential of Wi transpose X plus Ci. Okay. So now every Pi tilde is positive. Okay. Then I compute the normalization factor, which is, I call it capital Z. Okay, this Z is different from this little z. So the capital Z is the sum over all kinds of i's from 1 to k, P tilde I. So this is the normalization factor. Then if I divide Pi tilde by Z, then it gives me the probability, okay? It just satisfies all the things. So this becomes a predicted probability distribution that a particular sample can be categorized into different categories, okay? Is exponential of Wi transpose X plus sum over all kinds of i's. But now this time I would say this I call it j, okay? I just rename the variable to avoid the confliction with this I. So I call it j, exp, wj transpose x plus bj. Okay. And this function is known as the softmax function, softmax over C1 up to Ck. Okay. And the reason why it's called softmax is because, if C is higher, Ci is higher, then its probability Pi is also higher, okay? So it's similar to argmax, okay? If you are choosing the maximum value, then it's argmax. But now this time you are not choosing the maximum value. You are actually computing the probability. So it gives you a soft version of argmax, okay? So softmax is a soft version of argmax. And you can show that if you divide it by T, you can use the temperature to control that. If T goes to 0, then it's actually the argmax. Okay, so the reason why it's called softmax is just because it's a soft version of argmax. Okay, just a few terminology issues. This is known as the unnormalized measure. Okay, it's still a measure, but it's just not normalized. When you sum over all kinds of I for pi tilde, it gives you z. Okay, so z is known as the normalizing factor, or another name, partition function. And when you divide the unnormalized measure with the partition function, you get the probability. So this formula is very important, okay? So it's just the softmax. It's probably one of the most widely applied function in machine learning, okay? It's very important. And it's very easy to remember. You take the exponential, then you make everything positive, and you normalize it, and it becomes a probability. So there's no difficulty in remembering this equation, okay? Everything is fine. And if the candidate category is K, we sometimes call it K-way softmax, okay? Or a softmax function with K ways, okay? So this is the probability development for multi-class classification training. The training is going to be maximum linear estimation or with some penalties, okay? So the computation of the maximum linear estimation is homework, but I can show the loss, okay? The loss, again, is the cross-entropy loss, okay? So I'm talking about per sample loss. The total loss is the sum or the average of per sample loss. The per sample loss is minus t log, okay, pi. So I call it yi. And I make a summation for different i's. Okay. Okay. So here Ti is the 1-hot representation of the target. Okay. So I can say T, suppose I have 3 animals, okay? Cat, dog, elephant. Then K equals 3, okay, right? Then the target, I can represent it as a 1-hot vector, which is both T is in R to the power of 3. And it's more specifically, it's in 0 and 1 to the power of 3, okay? So if it's indeed a cat, then the T vector, so it's T1, T2, T3, okay? If it's indeed a cat, so it's 1, 0, 0 for a cat, okay? If the target is indeed a cat, then the T is this. Both T is this. Then T1 is 1, T2 is 0, T3 is 0. If it's a dog, then it becomes 0, 1, 0, okay? And if it's an elephant, then 0, 0, 1. So this is the loss, cross-entropy loss. And alternatively, you can represent it by J per sample loss. It's the same, okay? The minus log of Y of T, okay? And yi, okay, y is the predicted probability, okay? Y is y1, y2, y3, okay, which is the softmax of this. So this pi predicted is just the y, okay? So it basically says I use T1 times log y1 plus T2 times log y2 plus T3 times log y3. Okay, it gives me this term. Then it's the minus. And alternatively, you can have an index representation, okay? So I would say Jm for this sample is minus log of y index t, okay? So this y is a bold y for one hot target for the index representation of one hot target, okay? So basically, if it's a dog, then I would say my T is 2, okay? If it's an elephant, then my T is 3. So this is the non-bold T, the usual font T is just the index of your target. And now the Y is a vector, so you just take out this term and you take the log minus log, then it's the same as this term, okay? So basically you have K terms here, then K minus 1 terms are 0 for one hot target. Okay? So this is the cross-entropy loss for the softmax. And I haven't derived that. The derivation is softmax, and it's not difficult. It's just exactly the same as the binary case. And I think we have a good understanding for the binary case. Derivative. Again, this function is convex, and we don't have the closed form solution. And then we want to compute the derivative for that. It's again homework, okay? And I would say it's the same as this formula. It's the same as this, but this time you have a vector z. The z is no longer a, not this. So this time the z is a vector, right? You have z1, z2 up to z3 for three-way softmax. Then it will be the same as your prediction of the first way, second way, third way, minus the target of first way, second way, third way. Okay. Oh, but to prove that, it's the homework. Okay, good. We now know how to do the multi-class classification. It's just a small extension of the binary classification. We just use the softmax function to replace the sigmoid function. And then everything else is the same. And the loss and the derivative have the same or very similar format. Okay. So I will show that logistic regression is a spectral case of softmax. Okay, so I would say, what does it mean by special case? So actually, logistic regression is equivalent to two-way softmax. So let's assume I have two categories, okay, C0 and C1, okay. Then in softmax, I would say Y0 is W0 transpose X plus B0. Then I take the exponential, then I divide it by two terms, so I don't have to have the summation. I can just write it out. EXP W0 X plus B0 plus EXP W1 transpose X plus B1. And Y1 is EXP 1. Okay. Now I can say I focus on Y1. I can divide the numerator and the denominator by this term. Okay, then the numerator becomes 1. And the denominator, this term becomes 1 as well. Okay, so it's easy. Then this term becomes exp W0 minus W1 transpose X plus B1 B0 minus B1. Okay. And it's actually, I would introduce a minus term, then I will flip these signs, okay? W1 minus W0 X transpose plus B1 minus B0. Okay. Then it's obviously, it's a sigmoid function of W1 minus W0 X plus transpose B1 minus B0. Okay. And I can rebrand the W1 minus W0 as W, B1 minus BW as B, okay? So this is the sigmoid W transpose X plus B, which is the logistic regression formula, okay? So this shows that the model for the logistic regression is exactly the same as the two-way softmax, okay? Although the two-way softmax is over-parameterized, theoretically, you can just represent the weights for X as W, but now I say it's W1 minus W0, okay? But since in both models, they are convex, so the optimization will not be very different either. Okay. So this also derives the sigmoid function from softmax. So it says why we choose sigmoid function. We can say we would like use softmax to do binary classification, and then you can simplify things a little bit. If you only have two categories, then you get the sigmoid function, okay? But now the question is, why do we have to use the exponential function and then I normalize it by this, okay? Why not let's use another function? So this is my exponential, but why not let's use this? So the answer is you can use that, but then you lose the property. For example, the gradient does not have the nice form. And sometimes you don't have the closed form expression for this function, okay? So that's why we have the softmax function. Then it will derive the logistic regression in the two-way case. Inference. Inference just means your model is well trained. Now given a new sample, how can I make a prediction? Then I would suggest you just pick the category that is predicted most probable, okay? So given X star, then you compute Y star as the Y as a vector, okay? Y now is a vector. X, of course, can also be a vector as the softmax of, if I have a vector C, then I can write W matrix W X plus vector B, okay? Then I would suggest my prediction T is the predicted target is the argmax over Y star. Okay? It's equivalent to say the argmax of the predicted probability. Okay, it's the predicted probability that my target is indeed T. Okay, my target is indeed T given X. Okay, or you can write more compactly as saying the predicted probability that my target is T given X. Okay. So this is the inference. We just choose the most probable target given the input. So this is known as the max posteriori inference, or the map inference. Okay. So this is different from the map estimation. Map estimation is talk about the weights, and then you have the prior, and then you have the posterior. You pick the weight that maximizes the posterior distribution of your weights. here I'm talking about inference, saying the model is well trained, the weights are very well trained here. Okay, if you do the map inference, then you are going to predict the most probable targets given this data sample predicted by your machine learning model. Okay, that is known as the max posteriori inference because it's a posterior distribution of your target. You are saying, given the feature of this animal, what is the probability of my animal? You are not saying the prior distribution of how many cats in total, okay, all over the world for my pets. And why do we need to do that? Is there any other decision theories? Of course, you can, in the binary case, I mean, you can say a threshold, maybe the probability. In the binary case, the y is greater than a threshold t, then you can adjust the t, okay? It's not necessarily 0.5 to balance two classes, especially it's in the skewed class scenario. But I'm going to give some theoretical justification that inference is equivalent to minimize the expected error or the risk, okay? So suppose the true target, okay? The true distribution of the target given some data is pt given x, okay? Then my expected error, so my error, total error of some decision, my expected error where my expectation is set in terms of x and t, okay, is of course the expectation of x generated from p of x, okay, then t is generated by pt given x, right? Then what is the error? The error is your predicted label is different from my target, okay? This is the indicator function is different from my target. Okay, I can write things a little bit out. I mean, I only want to consider this part, okay? I don't want to consider x. So I want to say for any x, I have some probability. So I just write x out and I say t samples from t given x, okay? I've done nothing. But now I say for any x, I just want to focus on this term. The expectation of t sampled from given some x, okay? What is the target? So remember, the expectation of a function of something is the integral or the summation of the probability of your random variable times the function of that random variable, okay? So I can say t equals 1 up to k. Suppose I have k categories. P of probability of my target equals k, given x, times the chance that your prediction is not t. Why not let's make the accuracy, okay? It's more intuitive. So I would say it's 1 minus this term, okay? It's equivalent. but here it should be equals, okay? It's the accuracy. So this term is the accuracy, and this term is the error, okay? Then this term contains k terms, so I would say whether my probability t is 1 given x, okay, times whether my prediction is indeed 1 plus whether my prediction is 2 given x. Prediction is indeed 2, okay? So and so forth until you say my prediction is k given x. My prediction is indeed k, okay? And suppose you are not allowed to do stochastic prediction, you can only do a deterministic prediction. You only have one of h of x, okay? Then obviously you want to minimize the error and you want to maximize your accuracy. Then you want to pick the target that has the highest probability, right? Because you only have one vote, you either vote this or that, right? And you want to maximize this term, then obviously I just pick the most probable one, right? Then if you maximize the accuracy, you will minimize the error, okay? If you have a stochastic prediction, so I can say my h of x, okay, is, I would say, equals t with probability, predicted probability, I say h of x equals k given x, okay? Then you need to take the expectation over the h again, and when you do the calculation, it's again, stochastic prediction is no good, okay? Just like you have 0.2, 0.8, then you'd rather make all your predictions 0.8, then you get the minimum error, right? If you have, you get an accuracy of 80%, okay? If you have 0.2 and 0.8, then you have the expected error, which is 0.04 plus 0.64, then the accuracy is 0.68, okay? It's definitely less than your 80% accuracy. Then you have a higher chance of error, right? So if you take the expectation over h, you also show that if you have a stochastic prediction, it's no good. You'd rather pick the most probable category, and that will give you the minimal expected error, okay, for any x. But now I take the expectation over x, but for each of this term, so this is the expectation of x is the p of x dx, right? Then for the integral, if my integral, I have one function and the other function is uniformly less than the other function, then of course the integral of this function is less than that. So I would say for any x it holds, then if you take the expectation of x, it's still the minimum of your error, okay? So this shows that if you have the true distribution, then if you want to minimize your error or your risk, which is to maximize your accuracy, you'd rather choose the target deterministically by choosing the most probable target. And in here, we have a machine learning model. We don't know this. Then we choose the empirical estimate of your prediction. So this is the inference principle, which is to choose the most probable category predicted by a machine learning model, okay? In the multi-class case, then it's the argmax. In the binary case, you just say if y is greater than or equal to 0.5, then I predict t hat is 1, or otherwise t hat is 0, okay? Okay, very good. So in these two lectures, we talk about the discriminative learning for linear classification, and we talk about the logistic regression, the softmax regression, and their equivalent in the binary case. And we talk about the maximum estimation and how to solve the MLE. We also talk about the decision principle for inference, which is to do the max posteriori inference. Okay, thank you for watching this video. See you next time.